Hello everyone, we are Team Pi-Star Skyblazers. My name is Sheel and with me in this presentation is my teammate Sumedh. We are both grad students in the Department of Computer Science. First and foremost, we would like to thank the panel of judges for providing us the opportunity to present our findings on flight delay patterns. Let's take a look at why investigating flight delays is important. Remember the time when you went to the airport on a clear sunny afternoon and to your utter dismay, you found out that your flight was delayed. And to top it, you were left in the dark about the reason for the delay. Similar experience happens with thousands of travelers every year. Studies say that close to 20% of all flights are delayed, although 30% of these can be directly attributed to bad weather. What's astonishing is that almost 50% of the delays are due to factors that are under the airline's control. What makes matters worse is that there are studies that claim that airline companies sometimes lie about the cause of the delay to avoid paying compensation. Wouldn't it be cool if you could get some idea about how likely is your flight to be delayed in advance? Well, even cooler would be to know what factors are most likely to cause the delay. So the next time you have a flight delay, you know whom to throw the blame on. In our approach, we focused on achieving three major tasks. Number one, given the flight details such as the source, destination, date and time of travel, and the airline company, we developed a data-driven model to predict the expected departure delay that one may expect. Along with this, we also provide how likely the expected delay would be. Number two, we identified factors that contribute the most toward delays. This can be helpful in determining the key factors which can be controlled both by the traveler and the airline company. Finally, to put a cherry on top, we created a web application which displays the expected delay and the key factors causing the delay using our model.
Let's dive into the data and see what we can infer from it. Due to time constraint, we will just show some highlighted knowledge that we gain from the data. We can see that distribution of flights per company is pretty skewed, but the overall distribution of mean delays with respect to flights is fairly similar for most of the airlines. Therefore, we try to fit an exponential distribution to understand the behavior of delays as shown as by the formula on the top of the slide. So from the formula, we can say that we want A to be as high as possible, which denotes number of flights which are at delay 0 to 15 or basically on a lower side of delay, and then want B to be as low as possible, which denotes a sharp decrease in the frequency as there is an increase in the delay. So based on that, WN seems best as it has a sharp drop in the frequency of number of flights as we increase the delay, and EV seems the worst as it has a larger B. The figure to the left helps us to see a plot of airports versus flight carriers and the delays associated with it. It's worthwhile to see that the carrier EV has a lot of delay at many of the locations as we can see from the gray-brown boxes in its column. Similarly, some airports like Indianapolis and Minneapolis, New York experience some high delays. It is important to consider airport and source as a feature, as we can see that there is some pattern that we can observe clearly. To the right, we have a plot for AA airlines of mean delay at various source destination pairs. We can see that there is significant shift in mean and covariance for some of the routes. So you can consider for North Carolina in the picture, which strengthens our argument that source destinations are important for delay prediction.
Extracting non-obvious correlations in a large amount of data can be a Herculean task, which is where machine learning algorithms come to our rescue. For our analysis, we used random forests, which is a widely popular machine learning algorithm. The nice thing about them is that while being powerful, they are also very interpretable. The input to our model is a set of flight specific features. It outputs the delay interval and its confidence about the delay falling in that interval. Apart from the provided features in the data, we found that adding the mean of the past delays along a route and for a carrier specifically increased the prediction accuracy of our model. Let's take a look at the set of features that our model found useful. The figure on the right shows the importance of each of the features that we used as input to our model. As expected, the day of week the day of month of travel stood out. The relationship between the mean delays with these features can be seen in the plots on the left. The total number of passengers each month along a particular route and carrier also turned out to be a significant feature. The flight number is another such feature which implicitly contains information regarding the carrier, route, and the time of departure. These factors were also found to be important as explained previously in our data exploration section. The route and carrier-wise monthly net income turned out to be an interesting non-obvious feature. This relationship would have been difficult to capture without the help of a machine learning model. The mean delays from the historical data proved to be important features too. This is easy to infer since routes and carriers that historically have more delays can be expected to have delays in the future too. Let's look closely at how each of the features in our model affects the probability of a delay happening. The figure on the left shows the probability of the delay being in each of the delay intervals for a given trip. As we can see, the probability that the flight will be on time is the highest. Now let's analyze what factors are making this event more probable. The waterfall chart on the right exactly depicts this. The features with green bars are those which are helping the flight stay on time, and while the ones with red bars are those which are doing the opposite. According to our model, the flight number makes it likely to be delayed, while the fact that the net income is close to $41,000 helps it stay on time.
So we create a web app which would show you how much is your expected delay as well as the confidence score associated with it. We also show important features for the flight that cause a delay as well as those that help it to be on time. So here is a demo of our application. It allows you to look for the flight based on source, destination, flight date time, and carrier. Based on the current data available, it shows you the expected delay, if any, and how likely is that. It also shows you what works in your favor for the flight to be on time and what hurts more. If you are on a tighter schedule, for example, consider vacation where you have less time between the flight arrival and the event that you want to attend to. This might help you to choose other flight to avoid last minute rush as you plan your itinerary, or maybe even shift it by a couple of days if that event is still on going on. We would like to conclude the presentation with the following points. The data is highly correlated with the variables listed on the slide. Another important features are NAS delay and the late aircraft delay and traffic information along a route. The web app that we have developed would help the user to predict the delays way ahead of time and plan accordingly. Thank you for listening to us.